So our speaker today is Marcin Napiórkowski from the University of Warsaw, who will speak about the spin wave approximation in the quantum Heisenberg model. Please go ahead, Marcin.
So thank you very much. Thank you very much for the introduction. Thank you very much for the invitation. And also thank you for the job that you're doing in organizing the seminar. So even though I can rarely participate in the seminar, I always look at the videos on YouTube. So yeah, again, thanks for organizing it and running it. Okay, so today, as the title that you see on the slide says, I will speak about the spin-wave approximation in the quantum Heisenberg model, and this will be based on an older paper that I wrote with Robert Zeiringer and some more recent work that is hopefully soon will be on archive with Mateusz Kwaśnicki, Søren Petrat, and Michał Pietruszka. So there have been rather many talks on. Oh, let's excuse me. I cannot. Now I have to. Yeah. Okay. Sorry. Sorry. Yeah. Okay. So there have been probably many talks on spin system, quantum spin systems in the seminar, but I would say that my talk will approach these systems from a more traditional perspective of traditional statistical physics. So I will not discuss about quantum information. I will not discuss about some topological order. I would rather really, so what I have in the back of my mind and what motivates me and when I work on these issues is the question of long-range order in statistical mechanics and related symmetry breaking phenomena. Okay, so these are like central concepts in statistical physics that people were discussing for many years, and it seems that apparently there are not that many rigorous results related to these questions. So, in particular, the most important rigorous results are those of Frederick, Simon, and Spencer from 1976, where they considered the classical Heisenberg model. And they proved that there is a phase transition in this system when you look at dimensions 3 and higher. And there is off-diagonal long-range order in that model. So this is the classical Heisenberg model. Other results related to classical models are, for example, those that have been derived for n-vector models by Tadeusz Bałaban, as was in the 90s, which actually use very different methods, I would say. But on the quantum side, the most important result that we know today is the one from 1978, I would say, by Dyson, Lipp, and Simon, when they proved that the quantum Heisenberg antiferromagnet has a phase transition in dimensions 3 and higher, and that there is off-diagonal long-range order in that system. A model that is notably absent from this list, and this list is not exhaustive. I mean, there are many generalizations and results in various directions, but for those most basic models, I would say these are the most important milestone results. But the model that is absent from that list is actually the quantum Heisenberg ferromagnet. So I would say the most basic model that you would expect to describe the paramagnetic ferromagnetic phase transition on the most basic quantum level. And in fact, it turns out that I would say even much simpler questions and much, let's say, more basic questions related to this model are still open to this day. And the goal of my talk is to mention a few of them. I mean, mostly those which are related to what is called spin wave approximation, and also mention some of my contributions in that direction. So the plan of the talk is first I will define the quantum Heisenberg model so that we are all on the same page, and then I plan to discuss what spin wave approximation is. And then I want to discuss how can you make the idea of spin wave approximation rigorous, and I will discuss an approach which is related to equilibrium statistical mechanics, this will be related to the concept of free energy, And then in the end, I want also to mention the more recent work that I did in the context of dynamics of spin waves and how you can justify spin wave approximation from a dynamical perspective. Okay, so let us start with the definition of the model. We should think about the lattice. Let's say let's take the most basic situation when we consider a lattice ZD. So in D dimensions, we take the integer lattice and we consider a subset lambda of this lattice. So the subset is a finite subset of ZD. And let's say for simplicity, we assume periodic boundary conditions. We consider spin systems. So we have operators, the spin operators, which are the generators of the rotations in the 2s plus 1 dimensional representation of SU2. I will denote them by S1, S2, and S3, and they satisfy the well-known SU2 algebra commutation relations that are here, written out in the middle of the slide. So Sx here denotes the operators on side X. So Sx1 is the first operator of the triple, which acts on the side X, and the Sy2 operator is the operator of the second operator in the triple, which acts on the lattice side Y. Because the Hilbert space of the system is the tensor product over the lattice sides, so lambda is finite, so here there is no issue with defining this object. And on site, I mean, the Hilbert space on one single site is c to the power 2s plus 1, so it's a 2s plus 1 dimensional representation, as I said. In particular, if you set capital S equal to 1/2, so you consider spin 1/2 particles, then, on each lattice side you have a C2, spin up, spin down, and then all these operators that are written in this abstract form can be represented, for example, in terms of Pauli matrices. Okay, so I use this notation that the lower subscript X and Y, this will correspond to the lattice sides. And of course, when I write Sx, I understand this as an operator on H lambda on this tensor product Hilbert space, then I understand that this is the operator that acts as S1 on the X lattice side vector, and as an identity, it's tensored with an identity, so it acts as an identity in all the other lattice sides different than X. So with these building blocks, the quantum Heisenberg model is given by the sum of let's say unordered nearest neighbors pairs X and Y in lambda, which is the finite subset of ZD, and the sum runs over the terms. Here S squared is, it's a capital S squared, so S is the spin S that we choose. So for S spin 1/2 particles, this would be 1/4, and minus, and here the minus has an inner product between the vectors Sx and Sy. Okay, so this is the minus sign, which is here we have in front of this inner product, is exactly the one which makes this model the ferromagnetic model. So this means that, in general, we prefer alignment of the spins. And the reason why I introduce here the S squared underneath the sum is because I want to normalize this Hamiltonian to be, to have a ground state energy 0. Okay, so basically the largest possible value of the product Sx and Y is given exactly by S squared. This follows from the SU2 algebra, something that I don't want to discuss at the moment. And with this definition, the Hamiltonian is bounded from below by 0. Okay, so this is the well-known quantum Heisenberg ferromagnet. Okay, so as I mentioned, this operator is bounded from below by 0, so it has a ground state, and this ground state exactly corresponds to the energy 0. So what do we know about? Actually, there is not one ground state, but there are multiple ground states, because the Hamiltonian has SU2 symmetry, and this implies degeneracy of the ground state. But to fix our notation and focus, I would like to discuss one special ground state. Okay, and this one special ground state corresponds to the situation when we point all our spins on each lattice side down. What do I mean by that? Well, by this I mean that I introduce this vector omega state, which is a tensor product of the eigenstate of the third spin operator, which corresponds to the eigenvalue minus s, so the lowest eigenvalue of this operator. Okay, and exactly as in the this is the lowest eigenvalue. If in the case of S1/2, this would be just what I would call the spins pointing down. Okay, so this what I meant when I said that all spins point down here, because this is a tensor product, and on each lattice side we have the spins pointing down. And of course, as I mentioned, you can construct other ground states. For that, you use the operator ST+. So this is the total spin raising operator. So the operator Sx+ is the operator which is is a combination of Sx1 plus Si plus I Sx2. So this is the spin raising operator. And then with this operator, you can take a sum over all x's. This is the operator that would raise the spin on each lattice side. And then you can take powers of those operators, powers which are vary from 1 to up to the number of lattice sides multiplied by 2s. And then in this way you can form also one can check that in this way you can form other ground states. They also have energy 0, but they have, let's say, they don't have this beautiful interpretation of all spins pointing down. Okay, so again, here just a short reminder about the spin algebra. So if you act with an operator S+ on a state which, in which the spin points down, so which is an eigenstate of the third operator minus S, then you end up with a state which has an eigenvalue of the third operator minus S plus 1. So you flip a spin up. So in the case 1/2, it would be flipping the spin from minus 1/2 to 1/2. Okay, and somehow the notion omega, the notation omega here that we have in the middle is maybe not doesn't well, it has a reason. So sometimes this is called the vacuum state, well, maybe this interpretation hopefully will be clearer in a few slides. Okay, so we know already something about the ground state. Actually, we know everything about the ground states. But it turns out that this model has also a very explicit class of excited states. Okay, and these states can be obtained by raising a spin in a coherent way. So what do I mean by that? So recall that we have this operator S+. So we take the vacuum, so we take, let's say, all spins pointing down, and now we take the sum over lattice sides of the operators Sx+, but they are, we attach a plane wave to each of these operators in the form of e to the ikx. Okay, so in that way, this is what I mean, that this is a raising of a spin, but in a coherent way, and this coherence is somehow, via this plane waves. And then, of course, you need also to normalize it in an appropriate way. And here I introduce the notion of a SK+, which basically means that the SK+ is the operator of Sx+ e to the ikx divided by the square root of the number of the sides. So absolute value of lambda is number of sides in the lattice lambda, and SK+ is somehow an operator that is what we call a spin wave operator, because this coherent way of raising a spin is sometimes called a spin wave, and this state I will also denote by 1 sub k, in the sense that this is one spin wave with momentum k. So the k is now the momentum, and because I assumed periodic boundary conditions before, and lattice size is side length is L. If the lattice side length is L, then the momentum will be quantized 2 pi over L because of periodic boundary conditions. And then a short computation using the spin algebra will exactly show you what I said, that indeed those states, these spin wave states, are eigenstates, and the corresponding energy of such a one spin wave state is S times epsilon of k, where epsilon of k is called the spin wave dispersion relation, and this is given by this in 3 dimensions. Okay, I wrote it out here in 3 dimensions, but of course you can easily generalize it to any dimension. It's given by 2 times 1 minus the cosine of the vector k. So the sum of the 1 minus cosine ki, where ki is the ith component of the k vector. As you can, maybe one thing I will immediately mention here, you see that if k is small, then this has a expansion and approximation in terms of k squared, okay, which is the free particle dispersion relation. So as I already mentioned, this is what I will call spin waves. So these single coherent excitations of a spin over the whole lattice. Now, you could ask immediately a natural question is whether, well, can I maybe add more spin waves on top of this single spin wave? Okay, so I could just, take a SK2 or SP plus and act on this one spin wave state. So does this produce also like eigenstates? Yeah, with more, but the answer is no. So if you construct such states which has like NK spin wave states, so you would like to have this product, appropriately normalized product of SK plus to a power. So you pick your occupation numbers NK, and then you put NK particles into SK plus. So particles. So you raise the spin, or you produce NK spin waves for momentum k, and then you can have different momenta. So if such states, the question would be whether such states are eigenstates. They are not, and this already breaks down when you take NK to be 2, the sum of NKs to be 2. So already 2 spin wave states are not eigenstates of the Heisenberg Hamiltonian. But you can still do the computation and check what is the energy of such a state. Okay, because and in some sense, H lambda is almost diagonal in some sense on the set of those many spin wave states, and by that I mean this following heuristic equation that I wrote here in the middle. Well, that indeed, if you compute the energy in those many spin wave states, then a leading order term that you will see is the one that you would get from a set of like 3 non-interacting single spin wave states. Okay, so you take and you check how many particles are there in the given momentum. Like particles, I meant spin raising operators. And you sum their energies with which come from the corresponding aforementioned dispersion relation. But since this is not, there is an error term, and this error term is, it becomes complicated the more spin wave states you have. But in general, you can see a pattern that heuristically this error becomes small when you take the size of the lattice to infinity, so the more points there are in the lattice. And on the other hand, the error is also small if you think of very low momenta. Okay, so there is an interplay between momenta and lattice size, and somehow this error term, which can be very complicated for many spin wave states, but it has a general structure that you would expect it to, in some sense, say that it's small in the thermodynamic limit in the low energy sector. Okay, and exactly this heuristic picture is what motivates what is called the spin wave approximation. So neglecting those error terms, and treating those states, those many spin-wave states, as eigenstates with this energy, which is the sum of the single spin-wave's energies, is what we will call the spin-wave approximation here. And the expectation, you could argue, is the following. So if you think about low temperatures, so your system at low temperatures, then you should be close to the ground state. And if you think about the ground state that it was with all spins pointing down, then if you are at low temperatures, there shouldn't be many, I would say, excited spins, so not many flipped spins, because this costs energy, so there should be a low density of spin waves. And this means that there's a small number of excitations in the system, of those spin wave excitations. Because there are not many of them, this approximation from the previous slide should work, because of course this error term that I showed in the previous sum, of course, it deteriorates with nk in some sense. Okay, so this is not so. I mean, this heuristic picture is true only for a finite n, but of course, when you go to the thermodynamic limit, there is an interplay between nk and the size of the system. So basically, the idea for spin wave approximation is to treat indeed the system as non-interacting spin waves, and that indeed those states which have more than one spin wave can be treated approximately as eigenstates of this, in an appropriate way, as eigenstates of the quantum Heisenberg ferromagnet. We know that spin wave theory is not good when you approach the Curie point. So the Curie point, let me just mention this name. So the Curie point is the critical temperature when there is spontaneous magnetization, and which we expect to be true for the quantum Heisenberg ferromagnet. So, but this is not proven yet. So this is our goal, to prove it. But also we know that spin wave approximation would be not enough to prove it, because we know from our other arguments that this theory, spin wave approximation, breaks down. But still, I mean, I think that, as one of the steps, it is important to understand the limitations of spin wave approximation, and to really understand for how long does it really work, and to also understand how these spin fluctuations then, how their role increases as you go to higher temperatures. Okay, so and with this motivation, the goal for me and some of my recent work is to justify spin wave approximation in a quantitative way. Okay, so make this heuristic picture that I was just discussing more quantitative. And I want to do it in as I mentioned in the introduction, I want to do it on the level of thermodynamics, and also have a different perspective, a dynamical one. Okay, so let me now go to this thermodynamical perspective. And for that, let me remind you of the definition of the free energy, or rather the free energy density, because we want to analyze the system in the thermodynamic limit. So the free energy density is so first, for a finite lambda, we compute the free energy of the system, which would be, so we take the log of the trace of the Gibbs state. So the Gibbs state is e to the minus beta h. We take the log of the trace of that, we divide it by minus 1 over beta, and this would give us the free energy at finite volume lambda. And then we divide this by the size of the system, so the number of the lattice points, and then we take the limit lambda to infinity. This is our free energy density, and it depends on the inverse temperature beta, and it depends on the spin s in the model. Okay, so let me precisely write out that it depends on the spin s, because the Hamiltonian depends on the spin s. This will play a role in what I want to say next. So in 3 dimensions, if we would take this assumption that the spin wave approximation holds, and basically all excited states can be built up of those single excitations, which have a dispersion relation that I mentioned, which is the sum of 1 minus cosines, which for small momenta is related to, is approximated by k squared. then what you obtain from this computation is that indeed the free energy is given by this formula in the limit as beta goes to infinity. So beta going to infinity means that the temperature goes to 0. And here you might recognize a formula that you probably everybody learns in quantum statistical mechanics course, statistical physics course. So well, this is the free energy of a gas of free bosons. But so the beta to the power minus 5 halves, which is temperature to power 5 halves. So this is exactly what we get from the free boson gas in 3 dimensions, free energy. Here is also what pops up as the spin s, and it goes to the power minus 3 halves on the right hand. So this is the leading order term when beta goes to infinity. Okay, or maybe put it differently, if we divide by f of bs by beta 5 halves s 3 halves, then this is the constant to which our result converges, and this is the well-known integral also that you get when you discuss the free energy of free bosons.
But
so maybe the fact that we see, yes?
Shouldn't you have lattice bosons here with epsilon k instead of k square?
So this is a good point. So if you take the thermodynamic limit lambda going to infinity, this is, I mean, it's enough to actually, so to leading order, this is even in this regime, it's enough actually, you even get e to the minus k squared. Because actually it turns out that if you want to only look at leading order term, it's enough to take the limit when k is small. I mean, because the error that you get from replacing epsilon k by k squared goes into the next order term in the thermodynamic limit, because this is the limit when beta goes to infinity.
Thanks, yes.
But this is, yeah, I mean, yes. So, I mean, so this is yeah, so actually this is, I mean, exactly, this is, I wanted to make this formula here that these are really like free bosons really in R3, because this is something that everybody saw in his course, basically, I guess, in statistical physics course. But you're right. I mean, if you really want to think of bosons on a lattice that you will see in the next slide, then in principle, you would think of epsilon k here. But this goes, if you replace epsilon k by k squared, but at very low temperatures, this goes into the next order term in beta. So expansion. Thanks for this comment. Yes. Okay, so how to derive this formula? Because maybe, okay, so as I said, maybe the fact that we see the k squared here this is something that is maybe not surprising, because we already saw that you know, the spin waves have the dispersion relation that for small k behave like k squared. But the fact that this is a bosonic formula maybe is not so obvious immediately, yeah? Because I mean, in the end, we are speaking about spin waves. I mean, spins. So spins, you would maybe more think of them as fermionic objects, yeah. But still, we have the formula which you see for bosons. And to see why this is the case, I mean, it's useful to discuss about the Holstein-Primakov representation. So the Holstein-Primakov representation is a convenient representation of the SU2 algebra using creation annihilation operators on a given lattice site X. Okay. So again, so maybe before I go to these formulas, let me just introduce what we use to define those formulas. And so we have we have an AX dagger and AX, and these are the standard bosonic creation and annihilation operators on the lattice site X. Okay. So they act, you know, on the Fock space, let's say, I mean, on L2 of the natural numbers in the standard way that, you know, we learn in quantum mechanics 1 course. So the annihilator of Fn gives you n square root of n plus 1, Fn plus 1, and a dagger of F of n, it gives me, so actually here I'm mistaken. It should be Fn plus 1. Here the dagger and non-dagger, sorry, this is a misprint. But what is important, they satisfy the canonical commutation relation, so the commutator of NA dagger is 1. Okay, so if I have these bosonic creation annihilation operators, then I want to consider them on a subspace of the Fock space, which is the one which is related not to L2 of N0, the natural numbers, but only to L2 of 0 up to 2s. Why this? Well, because we know that our spin operators, I mean, we can have up to only, I mean, we can change the spin of lift the spin of our state only 2s plus 1 times. Yeah, so our spin, our local Hilbert space on site X is of dimension 2s plus 1, and this maps to creation annihilation operators acting on L2 of 0 up to 2s. Okay. So with these operators, we can rewrite the SU2 algebra in that language of bosons on a lattice. Yeah. So now let us start with this operator S3. So the one which for our representation of the ground state, we had that this is the eigenstate of Sx3 corresponding to minus S. So if we introduce the operator in the, we can represent this operator in the bosonic language by the AX dagger AX minus S. And then naturally, AX dagger AX has the interpretation of the number of bosons on the lattice site X. Now, notice that there is an important hardcore constraint. I mean, we know from the spin algebra that we cannot have more than 2s bosons on a given site. Yeah, so nx has always to be smaller or equal than 2s, and this is also like something that we see in the definition of this Fock space. Yeah, restricted Fock space, let's say. Okay, now we know now to represent s plus, s and minus, I have to introduce the square root of the operator 1 minus nx divided by 2s. And because I want to introduce the square root, what I have to take into account is the fact that I want this operator beneath the square root to be a non-negative operator, and therefore I always take the positive part of this operator. Okay, so 1 minus nx over 2s, positive part, and of that I take a square root. And with this definition, with this object, I can define s plus is a square root of 2s, ax dagger times this square root operator, and s minus will be 2s, the square root operator, times ax. So, and then this is an exercise to check that indeed these operators satisfy the SU2 algebra that we had in the first place. And we just use here we just use the CCR algebra of ax, dagger, and ax. Now, you see, I mean, this is well defined somehow, because when we look at S minus, or maybe look at S plus, so I mean, we know that if we have a state with 2s bosons, yeah, then we cannot, we cannot add bosons because we have this hardcore constraint. But indeed, this operator 1 minus nx divided 2s, when acting on a state with 2s bosons on site X, gives you 0. So here everything is well defined in that sense. Yeah. Good. And this is an exercise then to check that this is indeed a representation of the SU2 algebra. So now we have the picture of bosons on the lattice. And they can hop on the lattice. We'll see that in a second. But we always have this hardcore constraint that we have to take into account that we can have at most 2s bosons on the lattice side. Okay, so and then we can try to rewrite the Heisenberg Hamiltonian in terms of those hopping bosons. And now this is the explicit formula. So the first is an equality. And it's like a full formula, but the point is that now I wanted to say that, so from this formula, we want to take out a specific term, and the specific term that we want to take out of this formula is the one which corresponds basically to rewrite those square roots by 1, to add and subtract 1 from each square root. So those ones will produce us these terms that I have here. So ax dagger minus ay dagger times ax minus ay, together with this nx and y terms. And then everything else I will put into what I call k. So, and then when you do this, you recognize that this operator that I have singled out and I've written out and I call t is just the second quantization of the discrete Laplacian on the lattice. And this is the hopping term, so the kinetic operator for bosons on the lattice. Okay, so I will call it t. So the T terms really describes the bosons hopping on the lattice. And then if you look at K really, well, K, I mean, maybe a different way of looking at it, you can expand formally the square roots, in nx over 2s, and then you will see that the leading order term is 1, and this goes to the kinetic term, but all other terms which always will be of order 1 over s. Because this is an 1 over s heuristic expansion. And if you expand it, then you will see that it involves many body interactions, but of all orders, because, depending on how long you want to, use the Taylor expansion, you will have nx and y, you will have all powers of nx and y that you want, in principle, yeah? And this somehow corresponds to many body interactions of all orders, And in that picture, the spin-wave approximation really means that we neglect all these interactions and we only keep the bosons hopping on the lattice freely. And then you reproduce the formula that I showed on the previous slide. Okay, so how to prove this formula? And this is actually not so trivial, it turns out. So, there is a very famous paper, I would say, let me mention now some results. So there is a very famous paper by Freeman Dyson, which is called the General Theory of Spin-wave Approximations from 1956. In particular, Dyson computes the contribution to magnetization that comes from magnon-magnon interactions there. And there is a lot of inspiration that I believe mathematical physicists can take from this work. I do, but let me mention some also rigorous results, okay, which are related to this formula that I showed before. So people ask the question about what is the free energy of the system, but first in the large S limit, because you see, this rewriting of the Hamiltonian really tells you that if you have a limit of large S, so large spin, then there is some, there's a small parameter 1 over s in the system, and you can play with that and exploit this. So there are two ways to look at the large S limit. One of them dates back to Elliott-Heap from 1973, and this was also, there were like follow-up papers by Conlon and Solovey in the early 90s, and this is the limit when beta S squared is constant, and we call it the classical limit. Okay, and there is a different, so these were results that derived the free energy of the system in that limit, so in the classical limit for the quantum Heisenberg ferromagnet. Now there is a different limit which also corresponds to large S, but this is beta S with beta S being constant, and this is what is called the semi-classical limit. And in that limit, the formula that I mentioned before was proven by Correggi and Giuliani in 2012, and then later Niels Benedicter in 2016, he derived an upper bound on the second order term in that semi-classical limit. So why is this called a classical or a semi-classical limit? Yes?
Sorry to interrupt. I had a quick question.
Yes.
So before you said that the spin wave approximation, correct me if I'm wrong, the spin wave approximation was regarding the expectation of the Hamiltonian in these higher spin states with error terms that were negligible in the thermodynamic limit and large wavelength. But in the previous slide, it seems like we're taking the spin wave approximations, seems like it's analogous to large spin. I'm just curious how these
Yes. So I put it that way. So of course, how to say that? So of course, I would put it that way. So the formula that the question is, why can you neglect the? So the spin wave approximation really, if you look at okay, put it that way. So this is really that here we compute the energy, okay, and here we really have free like non-interacting spin waves, the leading order term that I put here, yeah. Now what goes into this error, yeah, this is something that I mean, I didn't write out what it is, but if you look at the thermodynamics, then you of course have to I mean, you take the trace of the Gibbs state, so you trace over all possible states, and the energies in that error terms, I mean, they will come from all different states, and basically you want to show that these states, I mean, that this K, I mean, it's not, I mean, in the real system, I mean, we have a fixed S, let's say, in the most standard situation, yeah. So you want to show that these contributions that come from K, they are indeed somehow negligible. But of course, this is just a rewriting of a Hamiltonian. Here, I did not evaluate anything on the spin waves. My point is that if you just take eigenstates of the operator T, this will be spin waves, single magnon spin waves, or let's say free bosons on the lattice. So you can easily construct those states, but these are not exactly the same things as spin waves. I just wanted to show here that in the rewriting that how you see that somehow how this formula appears, that this is a formula that is of bosonic nature. That was my goal, maybe. And then, of course, how you can somehow justify it. I mean, there are many different ways how you can try to justify it. Ideally, you would like to justify it for a fixed S. So then, I mean, this expansion, of course, is not valid, really, what I wrote here, yeah? I don't know whether this answers your questions.
No, I did. Thank you.
Okay. So maybe this will also shed a little bit of light. So okay, so that this beta S constant is what we call the semi-classical limit. And let me just mention why. Because so if you look at beta H, so the object that appears in the exponential when you have the Gibbs state, then if you rescale your spin operators by divided by S, then each of the spin operators is like of order 1, and they commute to 1 over S here. This is the second formula. So this is why we call them classical and semi-classical, because this rescaling of the spin operators produces a commutator that goes to 0 and S goes to limit. So this is why the limit when S goes to infinity is a type of a classical limit. Now, why do we distinguish the classical limit and the semi-classical limit? Because when you think about beta S squared, so if you take beta S squared fixed, as did Lieb and then Conlon and Solovey, then you have an order 1 temperature. So you reparameterize the temperature. So you redefine your temperature to be beta times S squared. It's an order 1 temperature, and you have a classical spins here because the commutator goes to 0. Now, if you keep beta S constant only, then your temperature is still very low because it's the inverse temperature will be F. So T will go to 0. The rescaled temperature will go to 0. So even though you have a system of almost commuting operators, yeah, you are at very low temperatures. So the quantum effects and the fact that they still do not commute, even almost, will play a role, and you will see quantum effects in that semi-classical limit. Okay? Good. But anyway, the bottom line is that both these limits, even though slightly different in nature, they both correspond to the large S limit. And this simplifies the analysis a lot, as my rewriting of the Hamiltonian on the previous slide hopefully suggested, because you have a small parameter which is a perturbation to the free behavior. Okay, so for when you consider fixed S results, then there is a work from Conlon and Solovey, a different one, where they kept S just equal 1/2, but fixed, and they derived an upper bound on the free energy in 3 dimensions. So the object that I mentioned defined a few slides before. And then 2 years later, in 93, Todd improved this upper bound, but this was still an upper bound that gave the wrong constant. So it did not produce, this integral that we have here. Much slower than I expected. Good. So, and then I would say, come the breakthrough paper by Correggi, Giuliani, and Zeiringer in 2013, where they proved that for any s bigger or equal than 1/2, but fixed, so they did not consider the limit when s goes to infinity, in the limit when the temperature goes to 0, so beta to infinity, you indeed get the asymptotics that spin wave theory predicts, and this is exactly the formula that I mentioned before. But this result did hold only in dimensions bigger and equal than 3. So now what happens in dimensions 1 and 2? So, well, of course, in d equals 3, I mean, it's not proven, but the big open problem in I would say, in mathematical physics is to prove that there is long-range order. But we know from the Mermin-Wagner theorem, basically, that in dimensions 1 and 2, there is no long-range order. So the physics of the system is different in 1 and 2 dimensions than that is in 3 and higher. And in some sense, this is also reflected in the proof. I mean, some things that go through in 3 and higher dimensions did not work in 1 and 2D. And a priori, it's not also completely clear whether spin wave approximation should still be valid in lower dimensions. And this is why we started working on this problem. And we were able to, already 5 years ago, prove a theorem in 1 dimension. So in 1 dimension, we have proven an analogous result that Correggi, together with Robert Zeiringer, we were able to prove an analogous results in 1 dimension. So we considered the XXX spin chain, so the quantum Heisenberg ferromagnet, for any s bigger or equal than 1/2. And for that, we derived the analogous formula in 1 dimension, which is given here. So note that when s is equal to 1/2, this is a very special case because the model is integrable. So you can use beta ansatz to analyze the XXX spin chain for spin equal to 1/2. But it turns out that actually using the beta equations, the beta ansatz and to use it to derive formulas or proof formulas in the thermodynamic limit is not so easy because I mean you have to get your hands on estimates on how the beta roots behave in the thermodynamic limit, and this is a complicated set of equations, and this is difficult. So in 1971, Takahashi proposed something which is called the thermodynamic beta equations. And using those, he derived the free energy of the system. Exactly, I mean, the leading order term in his derivation is the one that we prove here. So it's a low temperature expansion. And the approach of Takahashi is actually based on something that is called the string hypothesis, which is a very important concept as far as I know. I'm not an expert here, but it's an important concept in the community and in the theory of integrable models. But to make this hypothesis true or rigorous, I mean, this is still, to my best knowledge, an open problem, and I think there are even some counterexamples from specific models. So, I mean, it seems that this way of proving the formula only for s equal 1/2, where the model is integrable, is not the right way. So there are methods. There are also other expansions which use the integrability, but which are rigorous, but they usually focus on the high temperature expansion of the free energy. So, I would say the nice thing about our result is not only that we were able to prove the S1/2 case, but our proof also covers what happens for higher spins. Okay, so here I had actually 2 slides about the proof, but maybe it's a good moment just to skip this remarks about the proof, and let me just briefly jump to the question of dynamics. So I mentioned before that I would also like to address the question how to justify spin wave approximation, maybe from a dynamical perspective. So the idea is the following. So I consider now, so I know that single spin wave states are eigenstates of the Heisenberg Hamiltonian. Okay, this we know is a direct computation. So let me take a two spin wave state. Okay, so I take S plus and S plus with different momenta. Now, because I have only two spin waves, I can have a total momentum capital K, and I can have relative momentum little k. And then if you do the computation, and the energy should be close to that of those two spin waves non-interacting, so just to the S times the sum of the dispersion relation of the corresponding momenta. Okay, so this is exactly this capital EKK that I've written here in the second equation. And again, I recall that epsilon is the dispersion relation. And now the way I wrote all these objects is that I actually write that for k I have 2 pi k over L here because it's the quantized momentum. Okay, so what do I want to say? So, well, if this would be an eigenstate, if the two spin wave state would be an eigenstate with this energy EKK, then if I would apply to this initial state the full Heisenberg evolution, well, then then the state as an eigenstate would not change, and it will only acquire a phase. Okay, so it will only acquire a phase, and the phase would be, given by the energy of that two spin wave state. So somehow one could say that this approximation here in the last equation formula on this slide is what would be like a dynamical, prediction of spin wave theory. Okay, and our goal is to actually compare these two states. So we want to determine the time scales or have a quantitative bound for which the difference of those two states will be small. Okay, and this is the content of the next theorem that I want to mention. So, and here we are very specific. Again, we are in one dimension, and but more importantly, here we only have s equal 1/2 for our theorem. So we really are in the integrable world, and indeed, integrability plays a role in our proof. So, what is the statement? So we take an initial state, and the initial state is actually a bit more general than what I wrote before because it's a superposition of two spin waves states, and I will call it a two spin waves wave packet. And here this wave packet, just for simplicity, I assume that we cut off momenta that are, the momentum is like k over L, so we only assume that the momenta are small, and they are small given by a parameter epsilon, and this will be a parameter in the theorem. Okay, so the parameter epsilon, it says that we cannot, our momenta are bounded by epsilon basically. Okay, they cannot be too large. And now we introduce for this, two spin waves wave packet, we introduce the full evolution. So this is psi kt. So this is so here also, like when I said this, I fixed the total momentum of my spin wave packet, and I only sum over the relative momenta. So this is something that this is a theorem that we have already proven. Now we are still working on the extension to a spin wave packets that would also include the sum over those capital momenta k. But let me just flash that result that is written up to in all the details. So we introduce this full evolution. So the evolution given by the quantum Heisenberg model of this initial state, that is this two spin wave packet. And then I define what we call the free evolution. So the one that we would expect for each two spin wave state, so that it's, if this would be an eigenstate. So this is just the free evolution, which corresponds to the acquiring a phase, as I mentioned on the previous slide. And now I want to compare those two states in norm of the Hilbert space. Okay, and my theorem is that if you take L sufficiently large, and the capital K is fixed but finite, so it cannot grow with L, and you take some small epsilon, let's say smaller than 1/3, then what you get is that the difference, the norm difference of those two states to the power 2, is smaller than, we bound it quantitatively by two terms. So one term is the one which just corresponds, we call it to single excitation. So there always has to be something in finite volume, and it's just proportional to epsilon squared. But then there is the more interesting term, which somehow determines the time scales for which spin wave approximation holds in a dynamical setting. And this is the term that is now here, t squared epsilon to the fourth, and this is divided by L squared. So there is a 1 over L squared that is always present here, and this determines the time scales. Because we want, of course, we want to be much smaller than 1, possibly go to 0. So I mean, we want this norm difference to be going to 0 possibly, or at least to be very small compared to 1, and this determines up to which t's we can evolve our system and treat it as a system of non-interacting spin waves. The constants C1 and C2, they are independent of the parameters like L, K, T, and epsilon. Okay, and this is the theorem that we are now writing up, and I hope this will be soon on our. So some remarks about theorem. Well, I mean, as mentioned, so the time-independent term is non-physical for very small times, yeah. So because but this is, I mentioned that already, that as long as you have already one excitation and some interaction, there will always be this term. But this term will be if we assume that this term, this epsilon, so that we consider very small momenta, then this can also go to 0, and this also determines the time scales relative to the size of the system. Okay, so this is what I describe here in this remarks. I may be a little bit technical at the moment, so let me skip the details. But in general, the picture is that the smaller the momenta that are building up my wave packet, the longer the persistence of the eigenstate-like dynamical behavior. And importantly, this is something I had no time to discuss here. Of course, you can say, okay, you derived some bound, but actually we believe that our bound is in some sense optimal. We have a heuristic argument that will be explained in the paper that makes us believe that actually this bound cannot really be improved. Okay, and that's just two remarks on the proof is that, as I said, we use here the fact that the spin 1/2 XXX model is integrable by reducing our problem to an exactly solvable one-body problem for the dynamics. But what is mathematically maybe interesting here is that in order to get the timescales right, and this was something that we were really fighting for, that was our goal, those timescales that we think are optimal, that we believe are optimal, there we had to use some, we had to estimate singular sums, and we were able to do that by interpreting them as some expressions that can be described in terms of the discrete Calderon type operators and bounds for them. So yeah. So let me conclude. So I hope I gave you a review and an idea why we believe spin wave approximation is an interesting topic. And we've proven that the leading order term in the low temperature expansion of the free energy of the ferromagnetic quantum Heisenberg spin chain agrees with the prediction of the spin wave approximation. And we also, in a similar spirit, we provide a rigorous justification of spin wave approximation in the context of dynamics. What I did not mention is that actually our result in 1D also gives, where we prove an upper and lower bound, also gives the method of proof for the upper bound also gives a expected good upper bound in 2D. So for the quantum Heisenberg ferromagnet on the 2D lattice. However, a lower bound in the two-dimensional case is still an open problem, which I think is really interesting. And there are many other interesting things to do. I think, a very interesting question is what are the next order terms in the expansion? Even in the case, even in the large S limit, so in the semi-classical or classical limit, this is not this. I mean, the semi-classical limit, this has not been proven. Of course, one could ask the question whether the dynamics of spin waves can be, this estimates that we have, whether they are also correct for higher dimension or for more spin waves. So it would be also interesting to validate with numerics for dynamics which maybe are accessible via beta ansatz. And with that, let me thank you very much for your attention.
Thank you very much for this interesting talk. If there are questions or comments, please just unmute yourself and ask.
Okay, so can I ask a naive
Yes.
question? So you showed the first order theorem with Robert about the
Yes.
limit. Yes, about this free energy estimate in 1D. And as you said, the physics at finite non-zero temperature in 1D is totally different from that in 3 dimension. You don't have long range order. So what is the intuition between this proof of yours?
Well, the intuition is that this is really, I think here the fact that it's really that you really look at very low temperature expansion. And I think really that you only look at very small numbers of excitations. And basically because there is a small number of excitations and you still see free bosons only mainly. I think this is, so I think the fact that you don't have long range order is only starts playing a role at higher temperatures simply. Slightly, at slightly higher temperature. You're so close. Our expansion is really only very, very close to the ground state basically. Basically, yeah. I think this is although, there is already in 2D, this our proof does not work. So in that sense, our proof doesn't give that much insight because we clearly see that in 2 dimensions our proof doesn't work, and maybe understanding the 2-dimensional problem actually would give us more insight to see why the physics enters there really.
So don't you see anything like a scale, length scale, in which this naive spin wave approximation is valid in 1D?
Well, we have an explicit bound on the next order term, and in some sense maybe you could. We didn't do that, but I believe one could try to rephrase the bounds by determining the scale on which one has quasi-diagonal of long-range order, something like that. Maybe this could be rephrased in that way. This is a good point, yeah.
Okay.
But we didn't do that. Maybe this is something worth investigated. That would show you what are the scales really that you're asking about for, like.
Thank you.
For the correlation functions, you mean, yeah, like for the decay of correlation function or something like that. Yeah, maybe this would be useful. Yeah.
Okay, any other questions?
I have one, if I can.
Yes, go ahead.
So, what about the XXZ model?
So this is a very good question, and this is something that I want to investigate. I think the validity of spin wave approximation is less clear in that case, I think. Yeah, I think it's actually. So, for example, it would be interesting to see, in a quantitative way, maybe, when you put the delta in the coupling, yeah, like the one which is XXZ. So, for example, to see how the delta plays a role if you want to apply spin wave approximation. So, I think this is a very good question. Somehow we did. So I think I would first try to do it from this dynamical perspective. I actually was thinking about doing that later. I had nothing to report, and I think this is interesting because when delta is far from 1, then I think spin wave approximation should not really work. It breaks down. So it would be nice to see it in a quantitative way.
Yeah, I guess it's not very clear because you don't have the ground state as as clear as for the ferromagnet
Exactly.
for the XXX.
Yes.
But at the same time, one still expects somehow the spins to be aligned. So
Exactly. Yeah. So I mean, this is a very
for K small things might work.
exactly. So I mean, this is exactly that's what I mean. That would be interesting to see whether somehow quantitatively how this breaks down. Yeah. So with the explicit parameter delta, and if you have your bounds in delta, and you see how this goes into the bounds.
Thanks.
Thank you.
Okay, any other questions? Then maybe could we have a look again at this theorem about dynamics of spin waves?
Yes, here.
Yeah, I'm wondering if it's t squared, do you think it's optimal, or is it something what one could in principle get rid of?
No, so I think this is what we believe is optimal. I mean, really, this somehow we believe this is optimal. I mean, it's well, I think I'm not able to present the heuristic argument that we have now. But I think this should be. We believe this is optimal, and in fact, I'm planning to work with my colleagues physicists who use beta ansatz extensively on the computer, and we are actually trying to validate that bound actually.
Okay, but there are also some papers about scattering theory of spin waves. There are old
Yes.
papers from the 70s, and there is
Yes.
also a more recent paper from the 90s by Jean-Michel Graf and collaborators about asymptotic completeness of two-body scattering of spin waves. So if we had, I don't know if it's true, but if we have n-body asymptotic completeness of spin waves, then shouldn't something like this hold for all times?
Yeah, I mean, I think those. So I think this is. So this is. So the setup of their papers, I think, is in the infinite volume.
So you
And
think it's
I'm not sure how this translates into our bounds.
okay,
But
I
this is.
understand. So you are in
But I
fixed
think that
box.
this is I mean, this is definitely something that is. I'm aware of those papers, and in fact, actually now that I'm more into dynamics, I'm still, I'm trying to understand the results and how they relate. But the setup is slightly different there.
I see. Okay, and also I think I don't know 2 weeks ago or so we had here Simone Rademacher who was talking about the work with AV software, and to my
Yes.
limited understanding, it was about getting the T dependence of similar bounds better, ideally, uniform bounds in T.
Yes.
That's why I'm asking, but maybe
No, but I
it's
think
a different problem.
I mean it's I mean I wouldn't say it's a completely different problem, yeah, but I think here the picture is that simply the magnon interactions, they have to play a role at certain. I mean, if you take, I mean, at some moment they have to start interacting those magnons, yeah. And I think this would, I mean, this would destroy these bounds somehow. I mean, there are bound states of two magnons that that would. I mean, I don't think for large times this bound should not hold really, like for infinite large times. I don't expect this because there would be a formation of bound states of those two spin waves or something like that.
Okay.
And so I'm but I mean it's this is also like on the other hand, this is on the finite lattice. So the lattice size effect, I mean, this is I mean, we believe this is an optimal bound, but of course, this is only an estimate. And also, this is also a reason why we want to somehow test it against numerics and see what numerics say.
Okay, yeah, would be interesting. So, any other questions or comments?
I had one question, maybe slightly ambitious. Is regarding the higher energy spectrum of the uh, Heisenberg ferromagnet. So we know that the one spin waves give us exact eigenstates, and the low energy spectrum above the ground state. But these higher spin waves are not exact eigenstates. But do they maybe tell us something about what the higher energy states look like? So for the ferromagnet, we know that the ground state space is the maximal spin subspace of the chain, and you kind of expect to get higher energies as you lower the total spin. Do these higher spin waves maybe fit into that or tell us what the energies in those lower spin subspaces are or what the higher energy states look like?
No, I mean, yes, I mean, the idea is that indeed, I mean, if you think about the particle picture, yeah, that is indeed that you know, the ground state, there is no particles in it. So all spins pointed in one direction. This basically means there are no bosons on your lattice. But now each excitation, you put one boson, and if you only put one boson with momentum k hopping around the lattice, this is an eigenstate. But immediately when you, and this means you flip one spin in a coherent way. Yeah, I mean, you delocalize your boson on the lattice. Now, if you put another boson, then spin wave approximation says that this is close to being an eigenstate, yeah? But that this is not an eigenstate because those bosons interact. And you can quantify this interaction between those bosons. But I think, so this is flipping another spin, yeah? But then, of course, this, we don't know what is the exact spectrum of high energy states. I mean, we don't know what are the eigenstates, but somehow, you know, these theorems, I mean, at least the free energy theorem, I mean, it somehow makes you believe that at very low temperatures, when you have not many excitations, that, you know, it is enough to consider those excited states with not too many bosons hopping on the lattice or with not too many spins flipped. Of course, we know that the spin wave approximation will break down at higher temperatures. So at higher temperatures, you will have more spin flips, you will have more bosons, you know, hopping around. They will interact stronger, and then this breaks down. But at very low temperatures, this is, I mean, I think it's, you know, in some sense, you can indeed compute your energies in that way, in some sense. I don't know whether this answers your question.
Very much does. Thank you.
Okay, and other questions or remarks? If not, I would have one last request. Since you skipped some slides about the proofs, maybe you would be willing to tell us a few words about this proof. Well, we are not strict about the time, so
can you see my slides? Yes.
Yes.
Okay. So I skipped 2 slides. Okay, and these are 2 slides about the upper bound for the results in 1D for the free energy here. So this is the result.
I see.
I just wanted to tell you how you get this upper bound, basically.
Yeah. Okay. Go ahead.
So because as some say, there should be always one proof in a presentation. So this is like a, you know, a heuristic sketch how we do the proof, and the proof is just, you know, by picking a trial state. I mean, we are doing energy estimates. Yeah, I mean, free energy. We pick a trial state for the upper bound. And the trial state is what does spin wave theory say? Here, if you look at this, okay, so there is some technical method of localization in boxes. So for people who know about energy bounds for bosons or dilute bosons or whatever, this for them is very well known. And for those who never heard about it, don't worry. I mean, it doesn't matter. But the idea is to pick the right trial state. Okay, so we pick a trial state, and you know, we are at positive temperature, so we look at Gibbs states. Well, so the Gibbs state would be e to the minus beta h. Okay, but as I rewrote, I mean, h can be written as t minus k, and spin wave approximation corresponds to keeping t. Okay, so let us write e to the minus beta t as the Gibbs state, yeah? But then it turns out that of course, we have to take, so this, this is now formulated in terms of free bosons hopping on a lattice, yeah? So we have to introduce this, restriction that we cannot have more than 2s bosons on a lattice site, yeah?
Right.
So we have to project onto so we have to introduce this cutoff, which comes from the spin algebra. So we do a projection P, and the projection P is indeed this introduces this cutoff, but it does it in a slightly more complicated way that is heavily inspired by what Dyson did in his paper. Okay, so what we do is we take a smooth cutoff basically. So of course, if this function f of nx, it acts on this as a projector on the, x corresponds to projection what happens on the site x. And if there are more than 2s particles, then we just, this state is not allowed. So we have a 0 here, yeah? It's a projection onto, we need to have an x smaller or equal to s. Okay, but then it turns out that if we introduce a weight, which is at first sight non-trivial, but this weight means that we just project with weight 1 onto the states when there is no particle at that site. But if there are some particles on the site x, then we do it with a weight. Okay, in a funny way. So there is like a and this weight comes out from algebraic manipulations, basically. And this was also present in some sense already in Dyson's paper. Now, in the paper, with this projected Gibbs state of the free bosons on the lattice, normalized, yeah, which has to be a Gibbs state, we have the following lemma that if you compute the energy in that projection of the Hamiltonian, in that state, yeah, put it differently. If you compute with this projection P, the Hamiltonian, if you project on both sides, then you can bound it from above just by the kinetic energy T. So basically for an upper bound, now forget about the entropy at the moment. I will not talk about the entropy here in this sketch. This projection allows you to somehow extract in the upper bound only the kinetic term. Now, sorry?
Okay, yes.
So this is a computation. It's a computation, yeah? And now, what is different from the three-dimensional case is that in the three-dimensional case, Robert and Alessandro Giuliani and Michele Correggi, they used the same projection here, P, but they only had that it's 1 when nx is smaller or equal than 2s, and it's 0 when nx is bigger than 2s. They did not introduce this weight. And this weight is but then with this trial state only with this nx smaller than 1 cutoff. Sorry, I'm wrong. Sorry. They used only the cutoff. They had a very strong cutoff because they only put a 1 when nx was 0 or 1, and they put a 0 if there was more than 1 particle on that nx side. Sorry. And this led to a computation. So the same computation PHP could only be bounded from above by T, the operator T, kinetic operator, plus a leftover from the interaction energy. So by some bounds, they extracted that for the upper bound, they upper bounded the interaction energy in that trial state, after this projection P, by the sum over nearest neighbors of nx times ny. Okay? And this was not, and this is such a bound is not enough in one dimension or even in 2 dimensions, because think about it in the following way. So if you're in a low energy state, then you think that your density of the particles is very low. So nx is basically, you can think that the average density or the size of the operator nx is like 1 over L to the D. Okay, because L to the D is the size of the lattice. So you have basically the density is 1 over LD. It's almost uniformly distributed, almost no particles. And the kinetic operator, it has an energy gap like 1 over L squared because we are on a box, because it's basically the discrete Laplacian, yeah? And now if you compare, so if you take the sum over nearest neighbors of nx and y, then the number of nearest neighbor parses L to the d, because it's the size of basically of the lattice, small lattice. And then each of nx can be like estimated heuristically by 1 over L to the d. So you get a 1 over L to the 2d from 1 over L to the d from nx and 1 over L to the d from ny, which together gives you L to the 2d in the denominator. Now, this has to be, if we want to believe in like spin wave approximation and we want to see that t is the dominating term, we see that if you are in dimensions 3 and bigger, indeed this interaction term with this rough bound becomes subleading. Okay? But if you're in 1 and 2 dimensions, then in 1 dimension you have a 1 over L, and in 2 dimensions you're in 1 over L2. So this becomes comparable or even leading, yeah? So you cannot just have, so crude bounds, like very rough bounds on NX are not enough in 1 and 2D. And they were enough in 3D, in higher dimensions. This is the take-home message, basically. And to get rid of this whole interaction term, one had to play with this weight and use really some algebraic cancellations between terms which come somehow. There are cancellations from which is called kinematic terms and dynamical terms, because there are terms. These are terms coined by Dyson. So there is an effective interaction coming from the fact that we have hardcore bosons, that there cannot be more than 2s bosons on the lattice side. On the other hand, we have simply the interaction, like the real interaction that you have in your formula coming from the operators nx and y, yeah? And they compete, and there are some cancellations because they have different sides, and using this weight allows you to get these cancellations right. That's for the upper bound, basically.
Okay,
And the
thanks
lower
a
bound
lot.
is very specific to 1D. And okay, yeah, it's very specific to 1D, and this really doesn't go through in 2 dimensions. We use some kind of, we somehow translate the problem into a wave function representation, and we rewrite this problem in terms of a, like Schrödinger type operator in position space, but on the lattice, and use some estimates. And this works somehow only in 1D, because there is a mapping that we use that only works in 1D.
I see. Okay. Yeah, very interesting insights. Thanks a lot. Any other questions or remarks? Okay, if not, let's thank Marcin again.
Thank you very much.
Maybe let me stop the recording.